What we doing today will be we will be finish the last time we started of incompletion game. We have done the auction, but we haven't done the double auction. So just a few slides, and then we will do dynamic games of incomplete information. So topic 7 it will be something we are looking at. So very quickly, I hope you can see my slide. Oh, I can. You can see my slide. So so I think last time we just briefly go over the corner game of incomplete information, which I hope now you know how to solve. Just to remind you how this is being solved, is simply you can consider this as a multi-person game, right? Just like different type is a different guy, okay? And that is you solve by putting belief or probability on the other types, right? Say like in this case, right? Firm 1 and firm 2, right? Firm 2 have 2 types, right? Firm 2 we just maximize as usual as you do in Nash equilibrium. But firm 1, without knowing each type, which may be the cause of the firm 2, he's going to maximize based on expected utility, right? Expect the payoff, expect the profit from these 2. Okay, so I guess that would be the idea. Okay, so now so just to remind you what we see in the second price auction, right? Second price auction is the strategy would be truthful bidding, right? So everyone just bid his own or her own value, right? Second price auction, right? Because you pay only the second highest bid. So turn out to be, this is weakly dominant strategy, and that means it is part of the based on Nash equilibrium, because everyone is bidding their own valuation. It's an equilibrium, okay? And what we learn is if we have first price auction where everyone pays for his or her own bid if he wins and 0 if not, then the strategy is very complicated. But if it's a uniform, right? We know that the bidding is just going to be constant of the valuation, right? Is alpha. Then alpha is turned out to be depends on number of people, right? You just hide it by 1/n of your valuation, right? Just not bidding the all, but just part of that, because when you win, you still have some surplus, right? Basically, it's standard idea of marginal revenue and marginal cost, right? It's at this point, increase your valuation, right? Would just increase your chance, right? But you also are more likely to pay more. So we just make the surplus, you're indifferent at this point, okay? And of course, one important thing about this first price auction is that you have to know what others might think about the value, right? You have to assume the valuation of the others. The second price auction, you don't have to, right? So that's why it's somewhat easier in the engineering perspective, right? If you want make it easier for people, right, then you would want to do the second price auction, right? Because you can show in this kind of situation, actually you can prove by, I removed it from the slide, but you can show that the payoff for the auctioneer is no different between these 2 cases. That is a famous theorem called revenue equivalence, which I should have put here, but I didn't. But that means that you didn't care if you are a seller. But from engine perspective, I think you would prefer the second price auction because it's easier. for people to handle, right? Because a behavioral perspective, right? People would happy to join a scheme that is easier to handle, right? So that's why you see so many things as second price auction, right? So I want to, basically follow a textbook, right? You can see the treatment of the auction of this topic is very similar to the Gibbons textbook I'm recommending to read, because I think he do it very well in terms of exposition, because when you have incomplete information, often textbook make it very complex, but I think this is readable for this if you want to try to read it. So this is more, if you are from finance, that would be, there's actually a lot of time you see a lot of old papers, they use this kind of model, is the buyer and seller, okay? They are doing auction game to each other, in the sense that the you can imagine the buyer seller does for the stocks, right? Here is a firm and worker, but the more standard thing is imagine the stock market, right? And actually the stock market is actually double auction indeed. I mean, that's actually what happened in stock market in these days. Because in the old days, in the US, there's a dealer like the foreign exchange market. There's some guy stand there to trade with you, and he's control the bid-ask spread. But now there's no more middleman. Everyone can just submit bid and ask what price they want to buy or sell to the market, and that is a double auction. It means, and here it means that so let's set the setup. There are two buyers, so one buyer and one sellers. I mean, that can be imagined many buyer and many seller, but the case we focus on two, and how much they value the good is private information. You can imagine the buyer want to buy the good, initially have no good, right? He uniformly from 0 to 1, and the seller want to sell the good is how much he value the good is 0 to 1, right? If the case that the seller have VS is equal to 1, then no way that will be trade, right? Because it's always you keep the good, right? If the seller is 0, then it's almost always can trade, right? Because he will always trade out the good, right? So that's the idea. So in this model, do note that there may not be a trade. Okay, it need not happen to be trade, but that's the case. Okay. And if you're from real estate, that is also very standard. Okay, so in this game, right, we have to talk about strategy, right? Because this is a static games of incomplete information, so they have to simultaneously announce the price. Okay, so the seller want to put a selling price. Okay, that's called the ask price, which he's willing to sell the product, take the good to the other guy, to the buyer, and buyer give offer price P, right? The bid price, right? And there will be trade. Okay, if this buyer willing to pay more than the seller want to sell, and the price we assume to be in the middle. Okay, you can imagine there is a bargaining, which I should have time to talk about this tomorrow. Makeup, we do some bargaining, and basically you can imagine that they talk about how to split it, and it's natural to talk about in the middle. Okay, the middle one is not really crucial. Anything in the average will be fine. Okay, it's not something crucial, and actually you can prove, you can change all the proof here, just make any fraction be fine. Okay, but this you can imagine that the buyer seller are symmetric, so basically this end up in the middle. And what's the payoff here? Of course, there's a cosine linear, so you get the valuation minus the price, right? The seller get the price minus valuation, right? Just the standard. And if there's no trade, both players have 0 payoff. So the good is simply have no use to the seller. Okay. Okay. So if there's no trade, then the seller cannot keep the good. Okay. Of course, you can change the model, but this is what the simplest model you can imagine. Okay. So let's see what is the Basel-Nash equilibrium, right? So remember, this Basel-Nash equilibrium means taking the belief of what you think the others and the strategy right? Your expected payoff would be maximized according to your strategy, right? So that is the definition. It's bi-optimal, right? And what we have is the following. Let me go slowly because I think that has a lot of notation goes on here. Okay, I hope it's clear. So do note that here is not a price, but it's a function. Remember, is you have to give a price for each type. So that means, let's say from a seller, right? Seller can have valuation from 0 to 1. You have to map it to the price. It's a function there, all right? And same for the buyer, right? And there also have a buying offer price, also a function, right? So from 0 to 1. So it's not a number, but it's a number for each type. So that's why it's called a function. Okay. So so what the buyer do is choose a price. Okay. For each valuation, he will choose a price. So I pick up a valuation. Okay. What is the maximum? What is the price that he will give? Is look at his valuation minus this expected payoff, right? Times you can have trade. Okay. First, look at the second one. This is probability of the trade, right? You only have trade if your price is higher than the price asked by the seller, right? Is that clear? Is that clear for the second one first? First thing is your price is higher than the price given by the other guy. Okay? And what is the price you're paying is what you propose to be, right? And the other guy's price, right? The other guy's price is based on only if your price is higher than others, right? So because only if you're higher than your average, just conditional probability, right? Conditional expectation. Conditional on your price higher than other, what is his price? Okay? And you just flip for the seller, right? So that would be the case. Okay, so that would be the model. But let's actually see how we solve it. And in this model, okay, as we said, in general there will be many equilibria. Okay. So what kind of equilibrium we can get? And we only focus on two special case. Okay. One is called single price, one is called linear equilibrium. Okay, and that is very standard in finance literature as well. It's often you focus on these two equilibria. Okay, so the single price equilibrium is very simple, and you just say, and there's a single price. It's like later you will see today we call pooling equilibrium. Every type we just choose one point. So in this diagram, it just means this. It just means a flat line. Okay, you'll be thinking V of S, right? P, okay, and it will be something like, it's more like cut off. Okay, there's some X there, will be fixed at level, otherwise below that it will be 0. Okay, it's more like cut off strategy. Okay, you cut off somewhere. When the valuation is very low, you don't offer anything. Right? This would be 1. Sorry. For the seller, this is 1. Basically, you don't want to, when the valuation is very low, you just offer 1. Sorry. So seller will be like this. I'm sorry about that. Seller means if the valuation is low enough, then we just offer this. Otherwise, order very high price. And for the buyer, it will be like this. Also at X, V of B. Okay. When it's below, you will not buying it. Okay. When high is buying it. So this point will coincide here. Okay. So this is 45-degree line here. The 45-degree line here. Okay. And that would be the idea. Okay. What does it give us is only this, the price would be in equilibrium is X, right? Because the buyer is saying that, okay, whenever my valuation higher than X, I got offer X. Otherwise, I charge 1, right? And the seller and the buyer will say, okay, when my valuation is higher than X, I only have X, okay? And in that case, X is only equilibrium, and only when the buyer's valuation is higher than that we trade, right? Only if this thing occurs, right? Is that clear? So, do I have the graph here? I don't have a graph here. So you will see when you got a trade, suppose this is VB, this is VS, right? The trade only occur, suppose this is X, right? From 0 to 1 here. The space is only this, right? 0 to 1 here. So the trade will occur. This is 45-degree line here, right? This is X is here, right? Let me see if I have pen there. So trade only occur in this region. Right? It's only thing that trade will occur. Only for first, right? Of course, trade only occur in the lower triangle, right? And in this case, depending on what X you are talking about, that would be the outcome. And do note that there's an infinite equilibrium here. For every X is fine, right? X can be 0, X can be 1, X can be anything, right? X can be 0, which means that no trade will occur, right? In effect, only if the degenerate case, the seller thing is 0, right? The probability of trade is 0. And also 1, right, is also, and also the buyer is not going to buy anything, right? Buyer only buy when they think is also trade is 0, right? Trade you only maximize somewhere, you can imagine somewhere in the middle, right? And is it a good equilibrium? Probably not, because this equilibrium means anything is possible, right? So usually, and also we think this is not really not too realistic, right? Because there's some fix there, right? In the absence of other things, right? But you probably know, right? In many cases, if your social norm, that can support X, right? So, and you often see, right, in the case of marriage, right, 彩礼, right, is 60,000, right, in some places, right, 60,000 is the fix here, right? If you're poor, you don't get married, right? So that, right, only if you can pay more than that, you get married. That's what happened, right? And why X is 60,000, I don't know, right? There's a common thing there, right? And sometimes you may see this is the outcome, right? That's the only thing there. I mean, always, no matter what, I mean, in some area, they always ask for 60,000, all right? Regardless of, I mean, you have your money, you buy, right? You pay, right? And the seller is not willing to accept below that amount, right? And that is coming support our social norm, right? Social norm can tell us this is the outcome. Okay, so if you talk about finance, then that would be more better to focus on what we call linear equilibrium. Okay, in the case that the strategies may make a little bit more sense. Okay, And of course, we restrict ourselves to linear equilibrium, which means the following. Right? Just try to draw that, you will be see what we mean by linear equilibrium means this, right? My valuation here, what's my bidding strategy here? Sorry, my S, right? So let me do it slowly. All right, so it will be something like this, right? This is alpha B, this is my beta B here, right? So so this alpha and beta can be positive and negative. We don't restrict. The only thing is I only allow linear. Sorry. I guess I don't drink enough coffee this morning. Making a lot of mistakes, but hopefully it's fine. Okay. So that means that it's linear. Okay. And probably you ask why don't allow non-linear. Okay. The problem is when non-linear, the model becomes much more complicated to solve, and you can get most of the thing you want there. But the problem is even if you say I want a contracted one, it doesn't stop the referee to say why don't you try one more degree higher, right? So as always you can go further to ask this question. So as long as linear can capture what we want, that we stop there. And also is, I mean, probably you try to read the textbook, they will tell you that you can prove linear can be unique. Usually you can prove that, but it's very difficult to prove when beyond linear. Okay, so that's why I think the literature, I think that stop there, linear, and that's it. Okay. Of course, if you can prove something very general, then you go to top journal, right? But if you don't, then it's also okay, right? Then you just aim lower, right? So the first thing usually that's thing you show, the standard thing you show is if you try to show if one guy used linear, I also use linear, right? Then that's to establish the linearity, right? Because if other guy focus on linear strategy, I also use linear strategy, and you prove both sides, then linear is the equilibrium, right? And let's prove it, okay? And how do we prove it? We do it slowly. Okay. And here is assume uniform. Okay. What we assume is the seller also use linear strategy. Okay. And since seller use linear strategy, that means that because valuation is uniform, that means that the price is by the seller is also uniform. Okay. So that simplifies a lot. Right? Otherwise, you don't know what they're doing. Okay, so that's why you can see that is the reason why we have to restrict to linearity. If not, then this thing can be crazy, right? Then you have hard time to prove it. Then you need to resort to some functional analysis or some differential equation, which probably you don't have close form, right? That makes our life difficult. So that is our to find the optimal solution. This is what we do, right? Find the best P, right? You know your valuation, VP, right? Remember, you're maximizing for each type. So now you are VP, right? You know your valuation. So VP is you know it. So this is a constant for you, right? Because we're picking each type. So make sure that this is you, okay? You know yourself. What you do is you're choosing, you're evaluating this level, PB, right? So do note that PB affect two things, right? PB, increased PB will make you more likely to get trade. So that's the second part, the small bracket. But having higher BP actually will increase the price, right? So that's a benefit, right? Cost of benefit. So that's a trade-off. Otherwise, we'll go to corner solution, right? So I think that will make it clear what the PB does, right? Okay. So because uniform, right? You can just replace it by this one, right? Because that's how we do, right? You just minus the lower bound over the width, right? So that's uniform, right? That's, you can do integration if you want, but I guess just minus the lower bound and over the distance is the way you calculate the uniform, right? And The slightly difficult one is this conditional thing, right? But if you remember, that would be just because this is uniform, right? So how can we do that? Right? So it's like this, right? So you are talking about P of S is this guy uniform, right? So you're asking okay. So it's asking the probability that, so you know this is PB, right? It's coming from alpha S and alpha S plus beta S here, okay? So it's uniform here, right? The height is 1 over beta S, right? So the question is expected value of this, given this would happen, right? And what you do, right, is you know this is going to be true here, right? It's PB is your choice, right? You choose your P. Sorry for the typo. This is a PS, right? PS is uniform, right? This comes from here, right? And you are choosing your PB here, right? You move your PB left or right, right? The only trade is here, right? Because the higher the PB, you have more trade. If the PB is very low, as low as alpha S, then you won't have any trade, right? So probability of trade is actually here, right? You calculate expected price would be just look at this area, right? So this plus this over 2, right? You see this area, right? It's the middle point, right? Is that clear? It's okay? Oh. Average uniform, just bottom plus up divided by 2, right? Right? Because you seem puzzled, so that's why I asked, because no one responded to me, so I don't know whether it's clear or not. So we just turn out that this is a parabola, right? A quantitative equation. So you can have maximum, right? Second order condition will satisfy, right? Because it's negative, positive, right? So you can solve it, turn out to be linear. So this is a rather standard way to solve it, right? So you can see if the other guy is also linear, you do linear. You have to flip it, do it again, right? That is if the buyer is linear, the seller is linear. Then you can prove linear is equilibrium. So that's very important, right? You can't simply say, okay, let's have linear equilibrium, let's solve it. No. You have to show that if you are linear, I'm linear, you are linear, I'm linear, then you can solve it out. Okay? So this is rather standard technique, okay? Okay? You will show that if this linear, that's what I do, okay? And do note that the buyer, at the end, of course, depend on 2/3 of his valuation and 1/3 of what the seller doing, okay? And of course, you will be proving the same in the next, okay? Which I'm not going to bother you with the math, since if you do, you will have fun, right? Otherwise, you don't really worry about it. I mean, unless, I guess, yes. Oh, alpha S is saying that even though this is the minimum price that charge is reservation price. So alpha S is the reservation price of the seller, right? Even though I don't value the thing, this is the minimum price I'm charging. It's a lower bound. Or can be negative, need not be positive. Yeah, but in this case, it's positive in the seller, right? Seller can always make it positive. Right? This is the price I'm charging. Why? Because to extract more surplus, right? Because they're same as monopoly, right? Try to charge higher price. But we'll figure out what is alpha S and later, but you will see. I'm not going to bother you with that because this is just the same way to do it. But turn out this very funny. The seller strategy not only just depend on the reservation price alpha B, but also depend on slope. Okay, but anyway, that's what it is. Okay, turn out to be a very funny thing, right? Because the PB depend on alpha S only, not the beta S, right? But that is what it is. But probably because due to uniform distribution, but whatever, what we have is this is the result. Okay, and that means that you need to solve these two equations, right? Now we know that this is the best response from the seller. This is the best response from the buyer, right? You just plug it in, right? How do we solve it, right? This is the equation. This is the equation. Okay, and you remember also this is the result, right? So you can take it out. Is that clear? Okay, let me go slowly here. Seems like you don't. Okay, so this is the solution here, right? And do you know that only trade if this happen? Right? So that's why this would be happening. Okay, and probably ask how can I calculate the alpha and the beta here. Okay, so remember what we have is this. PB is what? Let me go back to here. Okay. We say PB is alpha B plus beta B V B, and PS is alpha S plus beta S VS. Okay? So compare this guy, compare this equation to this equation. You get this is alpha B, right? So is that clear? So alpha B is 2/3. Is that clear? Sorry, there's a typo here. And sorry. Sorry for a typo. That's why I said. So the first thing you would be, sorry for the typo here. So you look at the alpha B is this guy, right? So I'll look at this equation, you compare the constant term, alpha B is 1/3 of alpha S, right? And you compare this guy, right? And then beta B is 2/3, right? And then you look at alpha S is 2/3. And then you look at, sorry, alpha S. As I said, I don't drink enough coffee, so alpha S is this guy, right? Sorry for the mistake. Alpha S is 1/3 alpha B plus beta B, right? And then beta S is equal to 2/3 here. Okay. So we know now. We actually know the know this guy already. There's a constant here, right? You can just solve these two equations, right? Because no beta B, right? two equations in two unknown, linear, you know how to solve it, and that's you get the answer. Is that clear? Sorry for the typo. This is B, and this is S. Sorry for the typo. And that's the result. And of course, the number by itself is not super important, but what you can see here is like this. I should have put that in the slide as well, but I didn't put enough. But this is the suppose this is VS, right? And what's the PS here? PS will be 1/4, right? This will be the price they're doing, right? And the slope is 2/3, right? And what about the VB, right? If you try to do VB here, right, it will be something like this. It's 112. So that will be the linear function they do. Right? So, and if you try to draw the one we just seen that before, VB and VS in a two-dimensional, in the grid, right? You do remind that this is area you have trade. I'm not going to draw it. This is below, right? This is the area you trade, right? Suppose you trade, right? But now what you're actually trading is let's see, if I VS is 0, so 1/4 here. So only trade here, right? So VB has to be 1/4 more than that, right? So that means that there will be some trade not realized, right? Slightly different from the X. X is horizontal, right? This is like, is that clear? Right, because it's 45-degree line. So that means that I would also go down, right? This is 1/4, right? So that is how trade will realize in this model. Okay, so I hope, of course, all the calculation want to show you one thing is you try to how you solve in general Base-Nash equilibrium, right? When both sides have incomplete formation, right? And usually that you see in this case, even it's very simple. You can see that in general there are many equilibria, okay? And then you need to figure out how to construct an equilibrium to support what you think and what do you think is the most realistic one, okay? I probably think that in general, if without any social norm, this might be more reasonable, right? What you're going to say, this is just trying to say, right? The buyer would just think about what's my price I'm going to do, right? I just look at my valuation. I just take into account a little bit, 2/3 of that. And 1/3 depends on how the seller is, whether the power of the seller, right? How strong it is, right? How aggressive the seller is, right? Because the higher the alpha S, the seller is very aggressive, right? This is the reservation value, right? It's the minimum price they are going to trying to stuck things to you, right? And the buyer and the seller also the same, right? Look at my valuation. This minimum, I will do 2/3 of that, and I add some padding to that. Okay, so that probably is more closer to what you see. Okay, in the case where there's no social norm of what it should be, right? In the marriage thing, is as I said, there's a social norm that say 60,000, right, for the bride price, right? But otherwise, if you don't have the norm, usually that's what you may expect to see, right? But I hope that gives you some idea how we solve, because it's very common to see this kind of linear strategy when you think about base and Nash equilibrium. Okay, so I guess let's have a break here, and when we come back, like 15 minutes after, we will do the dynamic games of incompletion. We will define what is perfect Bayesian equilibrium, and we will do signaling game, and then Spence education model. Okay, so I'll see you in 15 minutes. So I guess we can resume. Okay. Oh, so by the way, I already uploaded tomorrow's makeup class material. So tomorrow we will talk about what I'm going to talk about tomorrow. Tomorrow I will talk about the allocation mechanism. Mainly talk about the context and bargaining, okay, which I think that would be useful for many business application. So context is more like the R&D or rent seeking. I mean, it's very common. And bargaining is how two agents to split a surplus. I'll talk about the next bargaining and the Rubinstein bargaining, which are the two main model you'll be using. But anyway, we left tomorrow. Okay, and so today we'll finish. Should be able to do it. Okay, we'll finish this dynamic games of income information. I would say this is even more difficult, and in terms of solving. But we'll give example, then you will see the difficulties lies on the fact that there's so many things to track, right? Because you can already see, right, when static game is very simple, right? Just players and strategy, you just check every possible outcome, then you're done, right? And dynamic game of compare information is just backward induction, right? You can solve everything very easily. Then since you look at the income information, you already see that you can't even really tell what are all equilibrium, right? We just focus on some equilibrium that we think is easier, we can solve it, right? In the previous case, the double auction, right? Is there any quadratic or nonlinear strategy which we don't know? Actually, we don't know. I mean, you look at the book, at least we don't know what are the set of all possible equilibria. We can say linear can be only units like this, right? But nonlinear, we don't even know, right? So that means that you can imagine when you go to dynamic, then the things keep on more ugly. Okay? And one more thing later you will see, the one more complicated thing is very important is what we call the solution concept is called the perfect Bayesian. It's simply the subgame perfect plus Bayesian Nash. Later you will see. Okay, but we will study these three concepts. But the main thing is because people take turns, okay, and information can be asymmetric, right? Because in the previous case, the Carnot case, right? Firm 1 doesn't know firm 2 cost, right? Firm 2 know his cost. But what firm 2, if firm 2 do things first, then firm 2 may reveal his information, right? The high type and low type may do the same thing, which don't tell us anything. Or they may do different thing, which might tell us something. Or they may randomize, which we also don't know as well, right? So that can be very complicated. And the guy look at what have been done previously can infer, right? So what his belief can change, okay? And it's very sensitive to the belief. So that's why turn out that game theorists think that belief now become very important. And also part of the system is endogenous because the belief is part of the structure, right? If you believe that's the case, then it will happen. Well, actually, there's, for those who finance, who know that is the idea of bubble, right? Bubble means that the value exists because people think they value it, right? It's not because of it value like this, because you think, or every people think that is to say bubble is supported by some belief, right? And belief should be part of the equilibrium, right? So how was the belief in the agent is part of the solution, So now it's different from before, right? Implicitly, we mentioned he has some belief in the background somehow, right? You talk about randomized in some case, right? In some sense, right? When we talk about randomization, rock paper scissors, right? You are thinking about the other guy is doing what they're doing, randomization, right? And here, belief is important in the sense that the equilibrium depends on belief. Okay, I mean, let me be more specific here. Okay, so I'm not going to talk about the formal definition because we never do it anyway. I try to put it here in case you want to take. But I think that it's good to motivate this, following the classical example, why belief is important. Okay, in this model, okay, player one move first. He can do LMR. Okay, in particular, he chooses R, right? Then the game ends. Okay, player two is not going to do anything. Okay, when player one chooses either L and M, player two would have to choose L prime, R prime. But player two doesn't know whether player one have choosing left or middle. Okay, so that's if you take away R, this is a simultaneous move game. All right, but the game change when player one can choose R first. Okay, when R, then it's over. Player two is not going to do anything. Okay, and just this simple change, right? And you can imagine, okay, this isn't we can impose some subgame perfection. No, because there's no proper subgame here. Only one subgame, right? Because there's no way you can cut such that it's a game itself, right? There's no way to cut, right? You cannot cut a player two. You can no point you can cut player one. You cannot cut anything, right? There's no subgame. Okay, and consider the following Nash equilibrium. There, you can write this as Nash equilibrium, right? Because you can list them out, right? Player one can use LMR, right? Player two is L prime R prime, right? When this is what happened, 1 3 1 3. LL prime is 2 1. L prime is 2 0 0, and this is 2 0 and 0 1. Okay, and now we have 6 outcomes. We can check all Nash equilibria, right? Which shouldn't be difficult for you. By now, you should know. You can highlight the one that is player one that will maximize his payoff, right? Okay, you do the same for the player two. Okay, you can easily check that L prime and R prime are both Nash equilibrium. Is that clear? We focus on pure strategy. Okay, is that okay for this one first? And economists, okay, have been arguing that R prime is unreasonable. Why? If you are player two, you look at yourself. What am I doing? R or R prime? So L prime or R prime? Okay? And you think the following. If you're here, you would choose 1 or 0. Maybe 1, right? If you are here, you would choose 2 over 1, right? There's no way, no reason in the world that you would choose R prime. Right? L prime is always the thing you do, right? But it's weakly dominated, or certainly dominated, right? But it's allowed in the Nash equilibrium, right? Do remind yourself when there is a normal form game, right? Static form game, this kind of thing cannot be in Nash equilibrium, right? Nash equilibrium, you cannot choose strictly dominated strategy, right? Never, right? But in this model, you allow. Right? Why? Because when R is chosen, 2 is never doing this, right? The payoff is never related to this one, right? So how can we solve this problem? Okay, economists would think, okay, you allow this because you are making unreasonable assumption on what 2 should be doing. 2 should be think a little bit more, right? He should have to assign belief on where the point is, right? Basically, this is allowed it because player 2 actually think these two is never possible, right? There's probability 0 on both nodes, but that's impossible. You have to be one of the node, right? You have to assign belief. You cannot assign 0 on both, okay? Because you think, okay, why this is reasonable? 1, 3 is doable because player 2 never think is here. Actually, he think he's there, right? Player 2 never think is there, but that is not possible, right? He must be somewhere in between, cannot be though there, right? So that is the reason we have to make player 2 have to say in equilibrium where he is, okay? He must be somewhere here. He must be probability over here. He cannot say, okay, no, I'm not here. Actually, I'm in the other universe. There. You cannot do that, okay? That's not allowed. Do you see the difference? Do you see the key here? Okay. So that is the main thing. You have to assign belief on where you are. So that means that if you, that is a definition of perfect Bayesian equilibrium. Okay. That is the most commonly used one. And you look at some paper, they will call it sequential equilibrium. Okay. And generically, when you talk about this, there's no difference there, okay? And sequential actually requires some sequence of equilibria convergence concept. So for most applications, it doesn't really make a difference, okay? So that's why we focus on this one. And look at the textbook, it's always it's also focused on that. But if you look at Mascola, Winston Green, or other advanced textbook, they talk about sequential. There's some slightly difference there, but for there's a paper talk about that. You should satisfy some regulatory condition. There's no difference. So since we're not really math people, so don't worry about that. So just do this standard definition. So in order to define actually require 3 conditions, okay? It's a pair of strategy profile, which we know very well. But the second way is we have the system of belief, okay? The first is the belief is well defined, which means that you have to, as I said, information set, you have to put probability there. You cannot say I'm not none of the location. Okay, you must say thing about one way or the other. There must be some probability over the node. And second is important is given the belief you have, your choice is optimal. Right? That is standard the Bayes-Nash equilibrium, right? Given the belief, your action maximized according to belief. Okay? The belief is meaningful, right? It's same as what we do in the Bayes-Nash equilibrium, right? Bayes-Nash equilibrium, your action is maximizing your expected utility that based on your belief, right? That's what this is. Right? There's nothing new there, right? So that is a thing we know, okay? So the first one is very simple, right? Just saying that there's a belief over information node. The second one is that based on belief, you do according to your belief, right? You believe this is the case, you maximize over that. That's very simple. The last one is the most tricky one. Okay, the last one actually is the most tricky and also the most difficult one is your belief updating along the equilibrium path is Bayesian. Okay, let me talk about what the Bayesian means. It's slightly little bit tricky. That means that your action. So you look at other people's action, you update your belief. Okay, your belief is not cannot be too stupid. That means that I would. Number one point is everything's belief. The last point is your belief have to be rational in terms of Bayesian. So that's why they're perfect Bayesian. What the Bayesian means is, let me show you. This is very simple in our context. It's not easy to explain, but let's see this example. Okay, and okay, why? First is why our prime is not the Bayesian-Nash equilibrium. Okay, it means because you have to put probability over the 2 nodes for player 1, so player 2, right? And no matter what P you assign, you always choose out L prime, right? Unless you put 0 on both nodes, but you can't, right? The restriction is either you put P on the left, 1 minus on the right, or one way or the other. You cannot put both 0, okay? But in that case, you would not choose R prime, right? You would choose L prime. This is gone. And here LL prime, okay, is a perfect Bayesian with the belief P to 1. So here is what the Bayes rule there. Okay, let me show you. Okay, the base rule said the following. Now, look at the equilibrium, how they would pay. Equilibrium dictate that this will be chosen. Okay, so what the Bayesian in the sense that you can easy to envision the following. Imagine this game played many times. But of course, you just play once, but imagine this game played many times. Player 2 would be seeing that L will be chosen after the game is over. Every time is L is the outcome, right? So if this is the outcome, if you play many times, you can only believe that P must be 1. That's a Bayesian, right? Because he would never observe M, right? If you play this many times. Only thing is reasonable, you believe is just only L, right? You cannot have probability assign anything other than 1. That's a Bayesian. Is that clear? Is that clear what the Bayesian? Okay, but put it this way. If player 1 is going to randomize equally over L and M, then the P must be 1/2. Oh, because R doesn't really matter. If, say, suppose in this case, if player 1 is randomized equally over L, M, R, then P is still also 1/2. That's a base rule updating. Because it's the base rule, right? And given the LM, what is L? Okay, suppose it's 1/3 here, 1/3 here, 1/3 here. Okay, you're here. It's just the probability L given LM is chosen, right? Is 2/3 over 1/3, right? So it's still 1/2. Well, in this case, right? Because it's randomly over this, right? Because, okay, put it this way. As I said, you just observe this game many times, right? For player 2, he know that half of them is L, half of them is M, right? If he had to think whether it's in L or M, it's 1/2, 1/2. Yeah, he's equally because he will think he will observe. Suppose he have observed 3 million around. He will observe 1 million around L, 1 million of M, 1 million of R, right? And because both are 1 million for L and M, he should, if they pay this time, he should think 1/2 is L, 1/2 likely is M, right? How to update this is Bayesian, right? Because given this conditional on, this node, what's probability of that? That's the Bayesian. But we will define more clearly later. But basically, just say you are not surprised. The Bayesian means you will not surprised by this choice, right? Is that clear? So the belief is, we can say Bayesian, right? Means the belief is consistent along the equilibrium path. The important is equilibrium path because in this case, only equilibrium is chosen. Here, okay. What's on equilibrium path here is if R is the equilibrium action, we don't impose any constraint on the P. You can call P whatever because in the wheel in this Bayesian, right? Because L and M never in the game. You never observe this, so you can put whatever P there. Okay. So that's why it's just my metaphor is. I said, right? Imagine this game played many times, or you observe, you update. Okay? But if then the game is not played, then it's not, you can't observe this, you cannot do it. Okay? So I can see this is very complicated concept. Okay? In general, that's usually how textbook would do is to give you a example, to illustrate the idea, you'll get what it means. Okay? So let's see the simple signaling game. And signaling game is so common in marketing, accounting, and finance that is always there. Okay, so a simple dynamic game of income formation. Why so easy? Because in this model, the informed agent move first, right? So actually, if you think about these cases, if the uninformed move first, actually the model is very simple, right? Because there's a backward induction, right? If you're informed that you know what to do and then just go backward, the model become trivial. So that's why the simplest example will be the informed move first, right? And what he do actually can help us to update our idea, right? You can see whether you're good or bad, can help us to review the information. So standalone game is very simple. How to define it? There's a sender, there's a receiver, and sender is going to send some message, M, big M, and small m will be the generic element. A is the action, and the type is only the sender type, okay? And the believer, we have some belief, and the payoff depend on the message, action, and type, okay? So what is it here? What are the example here is you can imagine is later we give example, but let's see this game, okay? This game. The game is played as follows, okay? It's very standard. Nature try to draw the type T, okay? And there's a common prior P of T, okay? And after the type is drawn, the sender learn his type, exactly which type, and he will try to design a message, okay? Do note that each type will send a message, okay? The message is type dependent. And then the receiver only look at the message and take action, okay? And the payoffs like this, okay? And the simplest you can look at it is this very crazy graph, okay? This crazy graph is the thing that we will use for this part of the class. So we will go slowly because it's very important to understand this graph. Understand the graph is the key to solve this problem, okay? So the nature will tell you whether you are the upper part or the lower part if you're a sender, okay? You can imagine this is a high cost or low cost, right? Cannot, right? You can imagine cannot competition, right? The new entrant is decided by the nature whether it's high cost or low cost, right? And the incumbent looking at what the message is sent, right? Maybe the new guy coming can do very expensive advertising or not, right? M1, M2 can be costly advertising or not so costly, right? And based on that, right? From the incumbent decide to fight that guy or just leave it alone, right? Some example like this, right? And this is the example, right? The sender, okay, can send a message, M1 or M2, right? Sender know who he is, but the receiver only know the message. Okay, the receiver actually don't know he is in upper level or lower level. Okay, but he actually know the message, right? The receiver know whether he's on the left game or the right game, but he doesn't know whether upper or lower. Okay, and given this, the receiver can choose A1 or A2. Okay, and here we assume that the action is independent of the message, right? Okay, can do, right? A1, A2, right? But so the sender, depending on type, can send message. Okay, so the sender actually has a 2 by 2, right? Each type, 2 action. Okay, and the receiver is action is based on message base, right? Based on the message, what you do? Oh, again 2 by 2, right? Message 1, what you do? Message 2, what you do? Okay, so that means that when you look at this, receiver only either choose this or this is a one possible choice. This and this have to be same, right? So left is A1 or A2, right or A1, A2. So it's 2 by 2. Okay. And as we said, the belief is important, right? So we have to say, after observing the message, we have to believe on the left-hand side, and the belief must add up to 1, right? That's a requirement. Okay. So this is the game. So let's look at a more elaborated one. Okay. So first is called system of belief. System belief require that, okay, mu, oh, sorry, typed the wrong thing. So it means that this plus this is 1, okay? And we also need this plus this is 1, okay? The first requirement, you must have belief, okay? If you don't know where, you have to believe. You cannot assign 0 to both, okay? Have to be apt to 1, okay? That's the first requirement. Second requirement is the sender, the receiver have to choose A1 or A2 based on their belief, okay? So that is a requirement here, okay? So that means that the receiver, okay, look at his belief, okay, and maximize, oh sorry, this T should be down here, okay? So we maximize his payoff, you expect utility, okay? And for the sender, okay, for the sender, okay, so actually I should put a star there as well, okay. Given the optimal action that expected to be taken by the receiver in the equilibrium, he sent a message that maximizes payoff. Okay, so that's, sorry, the typo there, but it's okay. So that, okay. And the last one is called the base. Is, as I said, right? You would be, this is a little most difficult to understand, okay? In terminology, right? But let's see the application that you see is very trivial, okay? But that's the standard Bayesian idea, okay? As I said, right? It's based on what has been chosen, and that is follow the probability. Just imagine this claim played many times, okay? Your belief should be proportional to what you observe, okay? So that is what it means. Okay? Standard Bayes rule idea. So usually in the literature, we focus on 3 types of equilibrium. What is the separating, pooling, hybrid? Separating means different types send different message. Pooling means that all the types send the same message. When you have pooling, the belief is very simple, right? Because nothing is as learned there. Okay, and hybrid will be combination of the two. Okay, the easiest to focus on separating and pooling, right? The hybrid is somewhat usually sometimes is there, sometimes can be important, but usually most of the intuition you can get is from separating and pooling. Okay, the hybrid is basically in the middle, right? So usually you already get all the intuition you got, so you don't need to worry too much. But to be rigorous, then you sometimes want to do that, because sometimes you see that as well. But you will see. Okay. So let's see this example. This example is very simple. Okay. First, let's see this setup. Okay. The setup is like this. Nature would have equally likely that the sender is type 1 or type 2. Okay, is that clear? That's a belief. So that is the nature. Okay. And the setup would be, okay, if the sender, okay, is type 1, okay, you actually prefer use up, right? Because this is pair, sender is pair 1, receiver pair 2, right? Sender the receiver want up, right? In that case, right? If I no matter what the sender do, okay, if there's left thing, I want up, right, to the sender. And for if the sender send right, that's a little bit different. Okay, So that means that the receiver actually would care what the type is, right? If I see L, right? If you see R, if L, then it doesn't really matter. I almost choose up, right? Well, of course, I prefer right? But if I see R, right? I have to guess what the type is, right? So that is the basic thing, right? If up is always good, then the game is very trivial. So the conflict is only when you see R, right? The receiver have actually some preference. Okay. Otherwise, if that's the case, right, that's always very simple, right? It'll be very trivial for the receiver. Right? There's some conflict there, and there's also some conflict as well, right? Because the sender, right, actually is very happy to trick him to do the down in this case, right? He tried to want to pretend to make him believe I'm here, right? Then I can choose the better outcome, right? If I'm a sender, I want to trick him this one, right? But if I send this one, then I end up in 2, right? So I actually want it to be this side is better, right? But this side is worse for the player 2, right? So that's why I have to be some conflict of interest of them. It's not aligned, right? If the interests align, then the model is very simple. Okay. But anyway, this is the game. We try to solve it out. Okay. And how do we do? This is the same way as we do in Nash equilibrium. We check all possible scenarios one by one and see what outcome can be. Okay. So it's very tedious, but we just do one by one, right? Just remember Nash equilibrium, right? Check every outcome and even DVA. But now it's more complicated. We'll check every outcome and check every belief. Okay. So let's now look at the case of separating equilibrium, which means that the different types send different signal. Okay. So now let's look at this one. Maybe I don't look at the solution. Let's go back and without looking at the solution and do step by step. Okay. So I said the sender do L. You can check solution, but I just do it here. Okay. The receiver do R. Okay. So that is we propose. Okay. Now let's do the base theorem first. Requirement 3. Okay. If every time you know sender 1 send L, sender 2 send R, you have P equal to 1. Right? And Q equal to 0, right? That cannot be anything, right? That cannot be anything. Looks like I didn't. This is 1. This doesn't seem to be I write anything. This is 1, this is 0, and this is 0, this is 1, right? This is what the base rule tells you. Why? Because you play many times. If you know the outcome, you know the player type 1 will send L, player 2 would send right? Then when you see left, you will think it's 1 upper. You send right, you know it's type 2. Is that clear for this one? Is that okay? It's the base updating. Okay? You just say your belief will be reasonable, right? Suppose this game play many times. Now we look at the receiver. What receiver do if he think is when the L is 1, then what you do? You would do U, right? You compare these two, you will do U, right? And if you are receiver seeing R, you believe you are below, what you would do? 0 or 2, you would do 2. Okay? So this is sequential rational for the receiver. The question is we ask sender. Is sender doing the right thing? Suppose you are sender 1, upper guy. If you send left, what you get is, right? Suppose I use the blue color. You sender 1, you send left, you get 1. If you go to right, then they wrongly believe you're here. You deviate, you also get 1. That's fine. I'm not deviating, same payoff. Okay? Now look at the case. I am a purple sender 2. Okay? Along the equilibrium I send here, I got 1. Okay? If I deviate, I send L. Oh, sorry. Sorry, I make a mistake. Okay, sorry. So go back to sender 1. If I send L, it's 1. If I send R, he thinks it's D, so I actually get 0. Right? Because it's above game, right? And sender 2, I send D, actually I get 1 here. If I send left, U is chosen because they think it's here, I get 2. Right? Then you would not do this. You deviate, right? Because suppose you are the sender 2, you would not do R. R only give payoff 1. You pretend to be type 1, send L, and which give you 2. Right? So that is not the equilibrium. So you cannot have sender 1 send L, sender 2 send R. Is that clear how I do this model? Okay. Let me do another one again so that you can see the logic. Okay, let's do slowly. Now, consider the case type 1 send R, type 2 send L. Okay? And according to the belief, this is 0, this is 1 here, and this is 1 here, this is 0 here. Okay? The base theorem. Now look at what is the strategy of the sender, so receiver. Receiver know this is 1 is here. Okay? He is looking at the payoff. Between 4 and 1, right? He will choose up. Okay? He don't know where he is, but he will, whenever he see L, he will choose U. Okay? And look at this. When receiver look at R, he believes that he will be in the upper guy he's facing. He just compare 1 and 0. In that case, he choose U. Okay? So that means that he will always choose U, right, in equilibrium. Okay? Now, we want to check the last thing. Is it sender to do this? Okay? Sender 1, okay? If he keep choosing R, in equilibrium, he got 2 here. If he deviate, choose L, he will got 1. So this is fine, right? If he deviate, right, U will be chosen. Right? He pretend to be lower guy. If he don't, right, that's cool. 2 is better than 1, right? And look at the sender 2. In the equilibrium, he will got 2. If he pretend he send R, he would only got 1. So this equilibrium. Okay? So in this equilibrium, we will have saying the sender 1 send R, sender 2 send L. The belief is that, and receiver 1 seeing L will choose up and R will choose up as well. Okay? And that is the complete characterization of equilibrium. Okay? Yes, question? No? So that's what I'm written here. So I think the proof is this one. Okay? That is how I do this proof. Okay? Now the next one is a little bit tricky because of the separating equilibrium. Okay, let me do this again to show you how we do separating equilibrium. Sorry, pooling equilibrium. Okay? Pooling equilibrium means the both types choose the same thing. Okay? Let's do one by one. Let's focus on the case both choose L. Okay? Both choose L. Okay? When both choose L, how do you distinguish P and 1 minus P? Remember, what do my base is, if we repeat the game many times, all right? Half of them will be type 1, half of them type 2, so you have expect P to be 1/2, right? Because right? So 1/2 is here, 1/2 is there, okay? So the receiver, how to calculate the expected payoff? If choose U, if he choose U, he will get either half of time is 1, half of time is 2, that's 1.5. You give him 1.5, right? And if you choose D, half is 4, half is 0, D will give him 2, right? So very clearly he will choose D. Okay? Now the problem is Q. What should be Q? You can't observe Q. So what kind of Q you can get? Okay? And what you should do if I don't Q? I don't know Q, right? There's no way you can justify Q. So that means that Q can be anything. In the perfect Bayesian equilibrium, you can assign any Q. And Q is crucial, right? Because if you think that the bottom is likely, then you choose D, right? The upper is more likely, then you choose U, right? So let's look at the expected payoff. If you choose U, right, then will be Q1 times 1 plus 1 minus Q times 0. This is Q. Right? If you choose D, then will be Q times 0 plus 1 minus Q times 2 is 2 minus Q. All right? So you can see that it is always true that 2 minus Q is bigger than or equal to Q. Right? Because 2 is less than 2Q, right? And 1 is bigger than Q, right? So Q is always less than 1, right? No matter what Q do, you will always do D. Oh, put it this way, okay? U is increasing in Q. Okay, let me draw a diagram. Looks not easy to see. Q is here, 0 to 1, right? This is a payoff. U is like this, right? Sorry. 2 minus 2Q. 2 minus 2Q here. Okay, that's fine. Then we require that, sorry. That means that, that means, right. 2 is bigger than 3Q. So as long as Q is less than 2/3, then you would choose the D. Okay? So actually there will be two scenarios, right? So when Q is very large, then you only if more than 2/3, then you would choose up, right? Otherwise you would choose down. So there are two scenarios. So that's why you can see very complicated even in this example. So depending on the Q. So let's look at the case first. First case, Q is bigger than 2/3, right? In that case, U will be chosen. So that's the case, right? So Q is more than 2/3, then U will be chosen, right? So now what we need to check is whether sender would want to deviate. Okay, your sender 1 in equilibrium actually get 4, right? Your sender 1, right? You're getting 4 here. Okay, so compared to the case when you get R, you get 2, so you don't deviate. Is that okay? And sender 2, you get 2 in the equilibrium. Sorry, you get 0 in the equilibrium, right? If you deviate, you get 1. So sender 2 will not send L. right? Sender 2 will say, okay, let's do R, right? Is that okay? Because sender 2 in the equilibrium gets 0. If he send R, he will get U, get 1, right? 1 better than 0, so this cannot be equilibrium, okay? So now we need to check another case, which Q is less than or equal to 2/3. In that case, D is chosen. Okay? Look at the sender. Send L, we get 4 again. If he go to R, he gets 0. So no deviation. Sender 2, in the equilibrium, he gets 0 again. But he will deviate, he will get 1. Okay? So there's no way that the sender will get L. Right? Because actually you can see even go checking, right? Because he's an L, he only gets 0. The worst outcome, right? But by going to this side, right, you get 1. Right? Actually, you don't even check this one, actually, easy. Right? Now we go to the other case. After this will break. So I see that many of us are very tired. So let's look at this one. Okay? Both sender. Okay? First thing you know, Q is 1/2. This is 1/2. Right? And look at the receiver. The payoff of this is U will give you 1.5. If you choose D, will give you 0.5. Okay, so choose up. Okay, the receiver always choose up. Now, same idea, we look at the payoff for when here, right? Will you choose up? Okay, will be P times 2 minus 1 minus P, will be 2 minus P. D will be, no, sorry, my mistake, because sender, okay, I did 2, right? So it's 3 times, it's 3.5. You choose this 0.5, right? So that means that upper will be chosen. Well, actually, you don't have to calculate, right? Because U is always better than D, right? I don't need to look at that, right? There's no way you can choose down, right? They always believe is up is always a dominant strategy. So now let's look at the sender. The sender, if sender 1 send out, payoff is 2. Okay? If you deviate to send left, you got 1. So no deviation. For sender 2, he's send out, give him 1. If you deviate, you get 2. So deviation. So in this example, there are no pooling equilibrium. Wait. Oh, sorry. There are no pooling equilibrium in this case. Yeah, that's right. Yeah. I look at the wrong result. Okay, that's fine. So now this is the way you solve this kind of model, and this model is very common, right? You can imagine there's an incumbent, entry and game, right? Or the M&A, merger acquisition, right? Or monopoly regulation, pollution problem, right? Because someone sent message first, right? So that is something very natural to see. Okay. After this, we go to break, and what we go after break is go to apply it to a more interesting problem, which is called the span signaling game. It's very famous as well. So what is different from what we have seen here is the choice become continuous, right? Before that, we have the sender have two choice, right? Left or right, up or down. But in this span signaling game, we allow two types of people who try to acquire education, okay? And level of education is continuous. And firm is hiring worker, the wage is also continuous, okay? It depends on education. I don't know the type, whether you're high type or low type, okay? I only observe education, okay? So that will be the model that the band Spence is doing. So we will talk about that. This is a famous model, and based on this, and then basically all the model is very similar to this one. So once you have this, then basically very similar. Of course, in application or when you apply it to write a paper, probably you want to get more complicated to get multiple rounds or other features, but you will see this capture the essence of the signaling game, right? Because after signaling, you can imagine they play some other game, right? But the game is solved similarly anyway. So that's a break of 15 minutes, and after that, we'll go to this very crazy signaling game. You will see very crazy graph there. Hopefully, but anyway, the graph will be enough for understanding all this thing. So make sure that you understand the graph later. Okay, that's a break of 15 minutes. We'll come back.
没有按区分类。不来也不好。
最常来的人最好看。
对啊，这个就在按照这个常来的。打电给他，自己没少说。这几个人另外一个。有个考虑，比如说，我会跟你说，我在去做不到的好，如果好的话呢，如果坏的话呢，我就跟你说，说话，不好的话就说，不止我说好的话，如果不好的话呢，不好的话，好的不好的话，我就跟你说，我就跟你说，这个不能我不能多讲话，还是我会有一半就是说，如果不好的话，刷一个。刷一个。对。如果不好的话，然后我再加一个地方，对。对，因为它是能力的，但是它不能说两个，但是它可以跟你说好的时候有好的时候有根本不告诉你才是你的需求。对，这个不太一样，他们是属于新的多，这是2009做了个然后最近的疫情。你的介绍吧。忘了。这两个部门，第二个是第二个。大家公共的这个关键是这个能简单。
就想说怎么把这个 green owner，
比如说这个 owner maximize choosing innovation。 green 的话，你可以很简单，比如说这个 green 的话，你可以说 high one，可装了 high one 就可以说 other price， other order， minus， 但是 green 呢是 green 就是在这里面。
这个的意思就是，如果你做 allocation 的话，它的
可以连锁，对，比较有好多种做法。第一个它影响到第一个它影响到没有开始就可以了。我一想到，要不然你就考试，要不然想 firm 的东西，要不然就。最细致的，他可以用他们可以这样，所以 some combination， 都不难的，你標啲 toy model 上嘅，開完之後就慢慢教，先多一點，先不要太技術，我會建議先不要太越來越。先來一個最多一點，然後開完之後慢慢再加。
你举个例子，对，就算在概率，然后选那个。
要不给你搞的。
这个容易乱，因为要分清。
对。已经讲全简单的，已经讲过就选择了，没人讲就。18有。18有2有，不应该真的真的真的。比如说最简单的 model， 比如说现在能够，比如说刚才最简单的模型，最简单的 model， 比如说因为会有的，也是可以的说，我在你的一块的，那个，然后他比如说告诉你他的情况怎么样，就具体来的。因为第二种就是说这个超级人，跟你的一块的，我跟你说，这50个人里面的都没有比较。 risk reference 看后面的有 risk reference 第三个300年买的但是这给你的那时候再问上在放什么多数的，比如说一个 menu 一个 menu 包括 item 对，我做DNA 啊，这半年，对，现在放得到，比较都是这个。有很多一些历史的，要不然100、300，有的钱
那个花费很多，而且
就是有多少最大的，就是说随便就简单来说说，康的可以比以前年代的时候高一个很质量的可以，对吧？还质量的就说那个有法的，你现在daily data 在发的这个做发放算是我不能发出来，需要就是说还做了个一般的这个，我也是一个不可能的一个运动类的对吧？你必有的可以的，再拿来个大的这种，有点新的，就是完全他们有一个这是每个地方都有，没办法。出生3年吧，他这个年代就是当地人没有36，根本就30，还得可以打一个第二个，而且 appendix 还有 appendix， 在 appendix 里面还有个 technical appendix， 就是这就是没有150页的这个，会放大一点，再大一点，但是就这么远，但是可以。所以就是要不然要不然就是一堆演的，没办法了，对。大这边就是哪部快掉了，我们没关系，黄庄的。
Okay. So signaling game. So once we're done, then basically the whole class is over, except tomorrow we have makeup. So
Again, that makeup is optional. Will be recorded as well. So let's look at the Spence model. So Spence model, I think is most relevant. It's also very controversial because what it's trying to do is trying to say that in this model, signaling, education is basically signaling, and education may not even improve our productivity, right? So it simply means that education is simply the way that we suffer. Who can suffer more? It's a signal, right? The longer we suffer, so that's better. But anyway, let's look at this game. So this game is the productivity of the worker is either high or low. The probability is Q. Okay, and in this model, okay, worker can educate themselves. Okay, and education is costly. Okay, the cost is C eta E. Okay, and of course, the more education you get is expensive. The more and more you get is even more expensive. Okay, why now you look at yourself Ph.D. right? One more year is very tired. Look, remember the year you spent in kindergarten, very happy, right? No homework, nothing, right? So the more year you got is convex. Okay, the very important in this kind of model is very important condition, which I should emphasize is called single crossing. Single crossing actually means the marginal cost for high type is lower than low type. Okay, so what it means by single crossing, which I think I spent many years to understand what it means. Hopefully you can understand right away. So basically it said this. Okay, it said if probably I I'll do that later. Sorry, single cross I'll do it later. But I just mean that the lower type have higher cost. I mentioned the single crossing later. But that is just saying that the high type is always better for the same education, right? You have more incentive to get education, less costly. And the model is you have two firms or more firms to make offer to worker. Why we want to do that? Because we want to simplify their offering, okay? So that they are in a Bertrand competition. They fight for the worker. So basically what we want is because later you will see the firm will make zero profit, okay? They are doing Bertrand, okay? And the output of worker depends on education and the type, okay? And obviously, high type is better than low type, okay? The more the same education, okay? And education is more useful for high type than low type. That's what it means, right? The last one. And worker is just wage minus cost, and firm is just production minus worker, production minus wage, and you don't have worker, you have zero. So that is the setup okay? Okay, and so as I said, competition makes sure that profit will be zero for firm. Why? Because it makes takes away the bargaining between firm and worker, right? So that is, you have to see how they construct the model, right? Spencer is very smart, right? To make this away, otherwise they will bargaining, right? And maybe you can, if you want to realize this, you can assume bargaining will be net bargaining, there will be surplus split equally, but we can talk about that next class. How surplus is being done in that one. But here is both, we will call it the symmetric equilibrium. In the case that if the firm, both firm, seeing the education level, they would think the product is the same. That means that they give the same offer. So basically symmetric, right? And that means that the expected productivity, right, will be looking at based on what he thinks is a high type. Oh, that's typo again, sorry. It's more minus, right? So think high type wage productivity, low type productivity. Sorry, I have 1 minus. Okay. Actually, what I want to do is either you take out 1 minus or this is high. It's up to you what you do. Okay. I'm sorry for that. Is that okay? So we just maybe use the high, maybe better, right? Because that is the only thing we do. So it's just easier to do this. Okay. Because we impose the baseline equilibrium idea, right? The belief will be must be up to 1. Okay. So in that case, only one firm because they're symmetric, right? So basically just only one sender and one receiver. Okay. So that's a sender receiver game. Okay. Although we have 2 firms, but that's basically 1 firm because we assume symmetric, 0 profit, right? So actually you don't have to only 2 firms. Infinite firm the same. Okay. So that's why Bertrand has some good thing is when the Bertrand doesn't really matter number of firms, so your model can be very general. Right? If you are willing to accept that it's a Bertrand competition, that means the surplus is much easier. Okay, so that is we often do this, and the problem, of course, how accurate is this guy, right? But that is another thing to do to say, right? Because in the real world, which is opposite the case, right? It's also usually if more worker than firm, right? It's actually the firm decide the wage rather than other way around, right? But you can imagine this is a case where there's a huge competition for the worker, right? In the old days, maybe in Shenzhen, right? Many people don't want, right? You have to get the worker, right? So that is important. But now things become more different. But anyway, not our concern. Now next is look at the following. Okay, let's look at the case as we would want to do in general is look at the case where there's no income information, right? Suppose firm is able to observe ability directly. So I know this is high type or low type, okay? In that case, the model become a dynamic game of company information, right? Because there's no income information, right? Suppose the firm able to see, okay, this guy is a high type, this guy low type. So we just need subgame perfect equilibrium. Is that clear? There's no uncertainty. Maybe uncertainty the type for the worker, but once the game is start playing, then everything is complete information, right? And in that case, because 0 profit, right? So worker just get paid the marginal. Sorry, get paid the output, right? Because Bertrand competition, right? Worker just get the output, right? If above that firm not willing to do it, lost money. If below it, other firm will bid up, right? So wage equal to output. Is that clear? Is that okay? So that's why no matter which education you get, you just get the salary, right? And what is the education you would get, right? Depending on your type, you just maximize that, right? And your wage is just based on that, right? Just very simple. Nothing new there, right? Is that clear? This is very simple model, right? This is subgame perfection, right? Is that clear? Here we do subgame perfection, right? Because we solve it at the last stage. What is the wage? And go back to education, what is optimal education? right? That's exactly soft barrier induction. Now we have more fun. Is look at the case. We will define two different cases, which is called no NV and NV cases. If the star denote equilibrium, NV case, no NV case means that in the equilibrium, lobe type is happy, the surplus of lobe type. Right? This is the equilibrium payoff for the lobe type. Okay. This is the equilibrium payoff for lobe type to mimic the height. Okay. In that case, we are done, right? Because it's incentive compatible, right? As you learn from the contract theory, right? You offer two different contracts, right? Lobe type in this education, this is the wage, okay? Total the lobe type. Then he not happy, he not mimic the high type. That's fine. The NV case have to be, if that's the case, right? The low type want to pretend to be high type. Okay? And that means that there will be some problem we have to adjust. Okay? So later you will see, but this is the thing we define, but we are not using it at the moment. That's the definition only. Okay? Let's look at this no NV case. Okay? What do we see is, suppose in equilibrium we have this. Okay? At some L, and this is the wage W star L, and H is this. In this case, we claim this equilibrium as long as this is satisfied. Okay? So what I mean is, okay, what we do is we pick up particular education level for the low type. This is positivity, and we draw indifference curve. Right? Everyone would want higher wages and less education, right? So just better in this direction. So this is that's the curve, indifference curve for the low type, IL. And if it's here, right, that's optimal, its tangent is optimal condition for the low type, right? So if you're here, low type, you get this wage, this is education, this is a wage you are facing, right? Because this is the wage that firm is offering in this one, then you are happy, you don't want to change anyway, right? And same for the hype type, okay? So for the single crossing, as I go back a little bit, backwards track a little bit. So single crossing means this indifference curve. The two line, high or low, only cut once. That is actually meant by single crossing. Means that the indifference curve, two indifference curve, high type and low type, if they ever intersect, only intersect once and no more. Okay? So that is the single crossing idea. Now, why this called no envy? Because look at this case. Okay? The low type actually indifference curve is better in this direction. Right? That means that the red outcome for low type is better than the green outcome. So in this case, the low type is fine. There's no deviation. Right? If not this case, the NV case, then it's not equilibrium. Okay? So we have to make sure that our equilibrium cannot have an NV case. If NV case, it cannot be equilibrium. Okay? This cannot be equilibrium in NV case, right? But whether this happens or not depends on the indifference curve where you intersect, right? Because the indifference curve can only intersect at one point here, right? Right? Because this curve is not, this curve given, right? Fixed. And this is increasing in this direction. So you can't really decide whether it cut off, all right? So it's either the case where cut off, right? Look at the optimal condition where the cutoff is there, right? So this is look at the complete information setup, right? Whether you want to have NV and no NV case, okay? So this is the setup of the problem, right? Independent of what is chosen there, right? So this is based on this complete information benchmark, right? Decide whether we are in the no NV case or NV case. You can see no NV case can be easier than the non-NV one, right? So this is based on the optimal condition, okay? Now, what we do is to show you, as we see, we will show you all equilibrium. We will check pooling, separating equilibrium, okay? And then we will try to say, in general, we want to remove pooling equilibrium, okay? Because pooling equilibrium usually don't make too much sense, right? Because you see why I study Ph.D., right? Because you are capable, you are high type, you want to signal it, increase the productivity, right? Or you believe other way around, but anyway. But that is the idea, okay? So let's look at the model. First is pooling equilibrium. Pooling equilibrium require you that everyone get the same education and hence the same wage, okay? And since everyone send the same education, which means that there's nothing to be learned for the firm, right? Firm would still keep the original idea. Q of them are high type, 1 minus Q low type. Q is the original fraction of the high type and low type. Nothing is learned. The base rule doesn't really matter, right? Because that's what we see, right? Along the equilibrium, base rule doesn't learn anything. Okay? And the wage will be just based on the expected productivity, right? Q of the time is high type with the education, 1 minus Q with low education. Okay? And there are many possible outcomes. We focus on this particular one, which said if I see if you get the pooling, okay, everyone got what they want, you believe you are Q of the time, you're a good type. Okay? But if you are not, okay, we make the assumption that you always low type. Okay? It's not reasonable, but it satisfies Bayes' theorem, right? Bayes' theorem means if this claim pay many, many times, what you observe. Because everyone at the end with pooling means everyone will choose the same education, right? Everyone said, I graduate from high school. No one get a college degree, right? If you get a college degree, then you think that you're crazy. That's fine, right? Of course, you will say, is it reasonable? That's not what we are doing, right? At this moment, at least, right? And what here we do is, in that case, if I saw you doing something nonsense, even though you get a PhD, everyone's supposed to get an undergrad or high school, then you just give low wage, right? Just think that, okay, I give you the low, believe the low type, right? So you give the salary like this, because why this? Why can I give lower? Because Bertrand competition, right? So everyone believes that you're low type, you got the low type productivity education outcome, right? And the education you get the pooling is just the maximize of this, okay? Depend on type. Okay. So what's the PB here? Okay. The PB here require you to say pooling for the low type, okay, is higher than the case that they would just do the low type thing. Okay. So let's see what we have here. Let's see the diagram. So what this graph shows the following, okay? This is the productivity, right? It's linear, okay? We assume to be linear for simplicity, right? And this is average productivity. It's a line, okay? And what is the pooling equilibrium? You have to pick one point here, right? Because Bertrand competition, the wage must be somewhere on this line, okay? And the high type cannot do anything because either you get this or you get the low wages, right? Because this is the wages they get, or you get this one, right? The high type cannot do anything, right? Because the firm, because it's a natural equilibrium, right? So if the firm offer this, what you can do, right? Because this is the wage stuff, right? This point must be higher than all this, so we don't need to check the high type, right? Because given the wage profile, and only need to check the low type, right? Low type is either he get this one or he get this one, right? Because this is a wage profile, right? This wage profile is given by Bertrand competition, right? And he just need to check if this point is higher than this one, right? Because if he do this one, it's okay, right? As long as it is, look at the indifference curve, as long as it's inside, then that's fine, okay? You can pick whatever point, there's many equilibrium there, right? And you may ask what are the possible cases, right? As long as you choose the wages along this up to the green, it's fine. All the green here are fine, right? You cannot be up at the green. Suppose you're choosing the brown, you cannot choose this wage here. That's not brown, right? You cannot be here. Why not brown? Because if you choose anything brown, the low type say no. I'm not going to get this much education. I'd rather to pretend. I'll just go to get the high school, right? Not going to there. Is that clear? So the pooling equilibrium say the following, right? The firm would always think you are low type, okay? But everyone would get some education, okay? And the firm would believe you get this education, Q of them are high, Q of them are low, or minus Q are low, right? And the high type actually cannot do anything, right? Because this is what firm is doing, right? And the low type, you just want to make sure the low type would not try to go away, right? As long as it's in the green region, that's fine, right? As long as green region, then things would happen, right? Of course, if you move the green region, then adjust the EP, right? Anything is fine. Is that okay? Is that okay? Now, it's the case where the simple is separating equilibrium, okay? That means that high type would get a high education, low type get low education, okay? When you see high education, you see his low type, it's a high type. When you see low education, low type, very simple, right? And the case is no envy, then it's very simple, right? Because no envy, just everyone got the efficient outcome, right? Low type just get what they're supposed to do in perfect complete formation. High type get what you get. When you do high type, then it's high, low type's low, everything is fine, okay? Everything is efficient, right? Because this separation is the best separation you can expect, right? And this equilibrium is efficient, right? Because by education, basically is perfectly aligned, right? That's good. That's the best outcome you can imagine, right? That is somewhat like the signal will actually solve the sorting problem, right? That's the best case. No wasteful resources, everything is good. So of course, It's very not interesting, right? So basically, this is what you get, right? The firm would be, look at the PhD, right? PhD above, you give the red one, right? If you get no PhD, then no matter how high you got, you just offer the low salary, right? And if you think that you get high is 1, right? Actually, I should write the 1 here. I should write 1 here to be, right? Blue to be 1. Okay, I hope that's clear. Is that okay? So because this is a belief, right? Because when I see education that is theta E star below, then it's low type, right? Is that clear? So this is most simple one. Of course, we go to the more crazier one. It's the case where if you do efficient, then it's not enough. Okay? And the natural candidate is look like this, very complicated. Let's see the graph. The graph look like this. Okay? You'll be the low type expect to do here. Okay? It's do the efficient thing. Okay? But the high type have to do extra. Suppose his originally is here, right? But he need to do extra, okay? Education, so that the low type don't want to mimic. Okay, and that is the answer. So what we're doing here? What we're doing here is like, because the low type want to pretend to be high type, right? What's the equilibrium is the high type actually do more education. It's inefficient, but in order to sort them out, there's a cost, right? There's also cost of making the exam too easy, right? You can see what happened now because everyone go to college, almost everyone go to college. So that's why you do the PhD. You don't become professor, right? In the old days, people don't finish the college, then can become professor, or the master can professor. But now we are not, right? Because everyone is going to college, right? In that case, I can't tell, right? Everyone can go to college, right? And that's why you need to do beyond. Everyone can do master anyway now, right? So you have to do PhD, right? And even in science, even worse, right? Many people do PhD, right? So you get the multiple postdoc to become a professor, right? Very soon, B school will be like this. Now it's happening in econ. People do multiple postdoc before they get a position now. It's like this, right? Because of the low type can pretend high type, okay? So you have to get extra education. You suffer, right? A little bit more. Of course, increase productivity a little bit, but inefficient, right? But that is how you separate themselves, right? How to separate themselves is to provide a little bit more. You have to do a lot more in order to signal that you're good. Okay? You can't really do it, right? Is that clear? Right? Just like in the old days, right? In order to date a girl, right? Maybe you just send some flowers, some chocolate would be fine, right? But now Tmall, Ali, Taobao is very easy to buy stuff, right? The cost is close to very little, right? So that's why you need to buy a lot to signal, right? In order to distinguish your Gao Fu Shuai, then, right? So you have to pay a lot. They pay a lot, right? It's very inefficient, but that's what happened. Okay, so what remaining 6 minutes, I want to show you two things. We have pooling and separate equilibrium, but we know that it's not efficient, especially for pooling. Pooling is the very inefficient one, right? Because the low type get education, which is inefficient, and the high type actually forced to be combined with the guy, right? And they want to stand out, right? If they're allowed to do it, right? Usually you want to convince that, okay, I got a PhD, right? you should pay me more, right? So that is what we're doing is we try to take away the belief of equilibrium, right? And we said what's the perfect Bayesian equilibrium? The last one is you only update when there's on equilibrium, right? Because your base rule, right? You just imagine the game play many times, just the probability just based on what you observe, right? What happens if you don't observe, right? And that's what we are doing. We are saying a message is dominated for some type, okay? If, okay, the best case scenario for one type, okay, for one type. So the worst case scenario for one type is better than the best case scenario, okay? Sorry. M is some message dominated, okay? In the best, it means that in the best case scenario, it's worse than the worst case scenario if I send out a message, okay? So that means that this message is stupid, okay? Even I envision in the world that there's a most favorable action to me, this is still not good, okay? Let me repeat this, it's a little bit convoluted. So M is dominated, means that if for some type, okay, if I do this, I envision the best of the world, which is the right-hand side, the max, right? And it's worse than that case. In that case, no one should assign the belief on the case I would do stupid thing. Okay? So let's see the example how this change our model. Okay? Actually, this will kick out many equilibrium already. So look at this. It will be okay. The things is what we try to remove is the following. Okay. Look at the low type. Let me draw a line here. Low type is here. Right? So if he is choosing the case where more than ES, okay, the low type more than ES, then it cannot be, right? Because look at the scenario, okay. So first we will say that if the firm saw education ES or above, okay, your payoff is worse than the L star, okay. So basically like this. If I saw someone have very high education, is it possible, any way possible, believe it is low type? There's no way, right? No way that low type would expect that would happen. So I must have the blue one. When I see things more than or equal to ES, it must be high type. Okay? That means that it would kill some equilibrium already. So let's see what equilibrium they kill. So you would only left the equilibrium like this. Okay? Why? If the separate equilibrium require this higher than the ES, right? Then anything between EH and ES must be the high type, right? Because remember this, okay? To support this NV case, we require this to be 0. Right? Cannot be high type. But low type can never choose this one. There's no reason that high type choose more than EH star. Right? There's no way that even though they expect the highest wages possible, right? That no way you can do it, right? So putting 0 here is not correct. This belief is infeasible, right? Because you can imagine the best case if you are the low type, right? Is there, right? So that's why you can't really happen to be that. Okay, the only thing is left is must be they're the same, like this. Okay, and the very next, sorry, a little bit overrun, but I want to finish this one. So the other case is pooling equilibrium depend on Q. Okay, why? Okay, imagine this low Q case. Low Q case means this line is more below, right? Because Q is low, then this average is closer to this one than above. Okay, in that case, right? Because we know that beyond it must be 1, right? And what happened here is the high type the indifference curve like this, right? And the payoff or high type is lower here, right? There's no way that he will choose the pooling equilibrium because pooling is somewhere here, right? Right? So the payoff, you should the firm should not have Q when it's here. You should have 0, right? Because it's dominated for the high type to choose the pooling thing. Okay, so the idea is following. Okay, if now because we have to Q1 must be here, right? So the payoff is somewhere here if you choose education like this. But choosing when Q is low, the indifference curve high type is like here. Okay, he will deviate because when deviate, he get this. This is the wages. He will choose this instead of here. Okay, put it this way. Okay, remember what is pooling equilibrium? Pooling equilibrium, how we sustain in the old days is the belief is 1 point here, everything is 0, right? But now with the domination, we cannot put this as 0, right? It must be 1 if you have very high education. So the main idea is the following. Okay, if you have very high education, okay, which is not possible for the low type to pretend you. So when you see very high education, it must be high type. In that case, if Q is very low, that means the pooling wage is very low, right? And then why I would at a high type I would not be doing that, right? I get low, I will get extra high education, so signal high type. Then it's better than the pooling outcome. Okay, especially when the Q is very low, right? Because right, there's very few high type. Okay, and this mixed wage is very low, although the cost is very low, but I'm not doing that. Okay, and if Q is high, you can still sustain, right? And if Q is high, okay, in that case, why it's true? Because if it's here, then I can draw the indifference curve for the high type. It's still above this one, right? So it's still fine. Can you see? So because when Q is high, the pooling equilibrium is somewhere like the I prime H, right? It's better than IH. Is that clear? No, because on the northwest side is better for everyone. So if you do now is because of the domination, so you must have red over there, the red line. So you can always get the red payoff. Okay, if you are, and if high type, then actually it's better there, right? But the pooling now is like a little bit actually better than you pretend high type. So the high type is still happy to do the pooling. Okay, but if Q is not high enough, then you cannot allow that happen. Is that clear? So I'm sorry that I want to talk about this last one. Sorry, this is, even though you don't get it, I have to talk about it because this is the very important idea. Okay, this is what we call equilibrium domination. Okay, equilibrium domination is slightly different. It's weaker. It requires that on the equilibrium payoff, okay, is better than the best case scenario. Okay, you compare to the equilibrium, it's the equilibrium concept. Okay, look at the equilibrium there. Okay, and look at the other cases. Okay, if other cases, the best scenario cannot be better than that, then the interpretive criterion that saying that you cannot have belief on that. Okay, let me show you the example. That would be easier to see. Why this is important? Because this remove everything except one equilibrium. The pooling equilibrium will be gone. So let me show you. Why no pooling equilibrium? Okay. So now we have a Q is very high. Okay. And look at the reason why there's no equilibrium here. Okay. So now we argue that, okay, this is average of productivity, right? And if you see the case lower than E prime, you think that this is high type, right? And you have to, okay, remember before we do that, this is here, right? Before that, we only have this guy, right? Maybe, okay? And until the criterion, what's adding here is this particular guy. Okay? The interior criterion add is this guy. Okay? So let's see what is actually doing here. The interior criterion, look at this. In equilibrium, suppose this is the equilibrium education, right? EP. Suppose it's pooling, right? And look at the indifference curve of the low type. It's the green one. Okay? It means that whenever I see E prime or above, okay, it can't be a low type, right? Because in equilibrium, the best is like this. Okay, along the equilibrium, everyone could do this. Okay, if I see education more than E prime, okay, between E prime or this, E must be high type, right? Because high type said, okay, I tell you the firm, okay, everyone got EP, okay. I said I have education at more E prime. I tell the firm, hey, look, the low type cannot get this much. Right? Even though the low type think he can get this education, he actually worse off. Okay? So when I get more than E prime, you should believe me, I'm high type. Let me repeat the statement. Okay? In equilibrium, everyone got EP. Right? Suppose equilibrium. And the high type said, no. Look at me. I have E prime. Right? between E and E double prime, right? That means that, okay, high type want to get, right? Because E and E prime still is feasible, right? It's better. And in that case, okay, you should believe me, I'm a high type, right? Why? Because low type, the best case scenario is no better than that, right? No type cannot pretend me. He do that, he'll be crazy. Even though you believe him is high type, he is worse off, right? Because low type is here, right? Low type getting this education, even getting a higher salary, will be worse than that, right? That's the worst part, right? So look at this. That means that look, this is a U star for the low type, right? Even the low type get the higher education, okay, the payoff is much lower because indifference curve is there, right? Because it's below it, right? So no way the low type will do that, right? So you should believe me when I get this, I'm high type. So that's the idea. Yes. Between E prime and we don't need. That's fine. We don't need to argue that. We just need to say that any deviation. So just try to make this happen. In fact, I actually don't need that, but just this only like this part. E prime and E double prime. So high type only willing to get E prime, E double prime, right? We cannot get more than E double prime. Okay. So high type would say, look at me, my education E prime, E double prime between somewhere. Okay, and you know that low type can never do it, right? Because in equilibrium, you're getting EP can only get this much, right? I'm getting so much education. Not a lot, but a little bit more than that. I mean, you should be me. Cannot be the other way around, right? So it must be the case that it must be 1. But in that case, it kills this equilibrium, right? Because everything here must be 1, then no one will get it. So basically, if you don't care about the math, it essentially said, usually, in signaling game, if you want to kill the pooling equilibrium, just invoke this interior criteria. In general, that will kill off that. Okay, this is a little bit more complicated, but the logic, but you can go home and check a little bit, but I would say every time it's very confusing, the argument. But the idea is very simple, right? Just say, okay, look at here, we'll be doing that. Okay, and what you left is just this one, right? Because we left this one and that one, right? So it's only equilibrium that survive. So that's what we predict, right? Always we have at the end we have separating equilibrium. Okay. So that's the end. Good luck. I will see you in the future. If you don't come for tomorrow's makeup. Tomorrow is FYB. No, let me see. YH. I forgot. Let me check. Tomorrow will be ELB. ELB is the econ department. Just no ELB. Oh. So look at the map. So this is the railway, right? So this is a railway. You go to the bus is in this way. You go the other side, go up the hill. The building is ELB. So like this. So you go. So this is the other side. Oh, this is our side. So you go to this. You go this way is our building, right? So you go. This building is ALB. So you go. This is the bus station, but you go up all the way. This is ELB. So you come from the station. Keep your left. Go up. Go up. Go up. And go this one up. So that would be the ELB. Okay. So I think I will see you tomorrow at 2:30 if you're coming. If you don't come, just the Zoom will be fine. Okay. So see you tomorrow. Good luck if I don't see you. So please try to hand in your project as early as possible because I have to. I know it's Christmas. It's 26th of midday because I have to submit the grade 27. So only half day. But so don't be too late. Otherwise, I would be have some problem.